Welcome to this deep dive. We're tackling a topic that, well, it feels like it's suddenly everywhere, doesn't it? Dominating headlines, conversations, even magazine covers you might not expect.
Definitely.
We've got quite a stack of sources in front of us here, reports, articles, some research, our own notes, all centered around artificial intelligence.
And that feeling you mentioned of AI appearing suddenly, it's a perfect way to put it. It really reminds me of that Hemingway line,
Yeah.
about how things happen gradually, then suddenly.
Ah, yeah, from the sun also rises.
Exactly. And that fits AI
Yeah.
perfectly, I think. Decades of gradual work, research building up, and then sort of, boom, it feels like it just exploded in the public consciousness. Everyone's talking about it.
Absolutely. We saw something similar with the internet, didn't we? A slow build, then whoosh, it changed everything. How we live, how we work, communicate. AI feels like it's hitting that kind of moment right now.
It really does.
I mean, just look at 2023. AI was on the cover of Time, Science, even Cosmopolitan, and The Economist, too.
Yeah.
Well, that's broad.
It signals this isn't just some niche tech thing anymore, right? It's touching so many different parts of life, different industries.
For sure. So our mission today, with all this material, is to really unpack it for you. We want to get a handle on what AI actually is. Then trace its history, which is genuinely fascinating, the key people, the big milestones, the different periods, the breakthroughs, and maybe figure out why it's grabbed the world's attention right now, specifically.
Yeah, the goal is to sift through these sources, pull out the essential bits, and hopefully give you some clarity on what's, let's face it, a pretty complex and fast-moving subject. Cut through some of the noise.
Okay, let's dive right in then. We really have to start with the basics. What is artificial intelligence? The sources give us a few angles.
Right. One core definition we found really focuses on a system's ability to interpret external data correctly, to learn from that data, and then use those learnings to achieve specific goals through flexible adaptation.
Flexible adaptation. That
Yeah,
sounds key.
it is. Because it's not just about following preset instructions like old school computing. AI learns, it adjusts based on the information it gets. It's dynamic.
That adaptability is the crucial difference. It's not just running code, it's learning and improving. And the sources point out there are different ways people have thought about defining this intelligence over the years.
Yeah, that's interesting too. Like, should we define AI based on systems that think like humans or systems that think rationally?
Or is it about acting?
Exactly. Systems that act like humans versus systems that act rationally. These aren't just academic points. They actually shaped different research directions. Was the goal to perfectly copy human thought or just get smart results, no matter how the machine gets there?
And there's a broader definition, the one from the high-level expert group on AI that AI Watch adopted. It seems to cover more ground.
Yes, that one frames AI systems as things designed by humans to achieve specific goals. They perceive their surroundings using data, they interpret it, they reason or process information, and then they decide on actions to reach their goals.
So perceive, interpret, reason, act.
Pretty much. And importantly, it notes they can use symbolic rules like classic programming, or they can learn numerical models from data, like machine learning does, and they can adapt their behavior as they go.
Okay.
And it positions AI as this big umbrella discipline. It includes machine learning, and under that you have deep learning and reinforcement learning, plus machine reasoning and robotics. It's a whole field.
Got it. So AI isn't one single thing, it's a collection of approaches. And within that, the sources break AI down into three main types. That seems helpful for understanding what we're dealing with.
Definitely. The first type, and this is the one you encounter most often, like day to day right now, is artificial narrow intelligence, ANI.
Also called weak AI sometime.
Right, weak AI. This kind of AI is really good at performing one specific task, or maybe a few related tasks, but only within a very specific limited context.
Okay, like the voice assistant on your phone, Siri or Alexa.
Perfect example. They're amazing at understanding your voice commands, setting timers, playing music, answering simple questions. But, ask Siri to write a symphony or diagnose an illness. It can't do that. That's ANI. Powerful, but narrow.
So specific tasks, what are some other examples from the sources?
Well, AI medical systems that are trained to analyze, say, medical scans for signs of cancer, language translation tools, the recommendation engines on Netflix or Amazon that suggest what you might like, image recognition software, Face ID on your phone, even those robots you sometimes see in factories doing one repetitive task, or One source mentioned a hotel robot that brings things to your room but can't, like, help with your bags. All AI. They do their job well, but that's their only job.
Competent but focused competence.
Mhm.
Okay, so that's what we mostly have today. What are the other two types? They sound more future-oriented.
They are. The next level up is artificial general intelligence, or AGI, sometimes called strong AI.
AGI. That sounds like the sci-fi stuff.
Pretty much. AGI is the hypothetical goal of creating AI that has the ability to understand, learn, and apply its intelligence across a wide range of tasks. Basically, performing any intellectual task that an average human can. Think Data from Star Trek, maybe.
Right. Multi-talented, adaptable intelligence.
Exactly. But, and this is important, the sources are really clear, AGI does not exist today. It's still a massive research challenge. We're not there yet.
Okay, so ANI is now, AGI is the future goal.
Mhm.
And the third type,
It's artificial superintelligence, ASI. This is, well, it's intelligence that would vastly exceed human cognitive abilities in almost every domain imaginable.
Mm.
Creativity, problem solving, wisdom, you name it.
smarter than humans in basically every way.
Yes. And the sources interestingly note that if AI ever gets really good at generalizing knowledge or understanding cause and effect, it might actually lead closer to ASI than just stopping at AGI. Because its raw calculation speed and memory are already so far beyond ours, why would it limit itself to just mimicking humans?
That's a slightly unnerving thought. But ASI, like AGI, is still firmly in the realm of science fiction for now.
Absolutely. Speculation, sci-fi. Not something we have.
Okay, good to clarify. So the spectrum is narrow AI, ANI, which is powerful but limited, that's what we have now. General AI, AGI, matching human smarts, that's the goal. And superintelligence, ASI, exceeding humans, that's theoretical. ANI is where the action is.
Exactly. Understanding those distinctions really helps frame the conversation about what AI can do now versus what people hope or fear it might do later.
Right, so now we know the types. What actually makes these ANI systems work? The sources seem to point to three essential ingredients.
Yeah, they frame it almost like an equation. AI needs algorithms plus data plus compute. You need the smart instructions, the algorithms, you need tons of data for them to learn from, and you need serious computing power to process it all.
Algorithms, data, compute. Okay, let's break those down. Starting with algorithms, you mentioned machine learning earlier.
Right, machine learning, or ML, is absolutely central. It's the core idea of building systems that can learn from data without being explicitly programmed for every single possibility.
So they figure things out themselves by looking at examples.
Pretty much. By analyzing huge data sets, ML systems spot patterns, build models, and then use those models to make predictions or decisions. Think weather forecasting, or recognizing faces in photos. The system gets better as it sees more data.
So instead of a programmer writing like a million rules for what is spam email, you just show the ML system tons of examples of spam and not spam, and it learns the patterns itself.
Exactly that. It induces the rules from the data. And within ML, there's been a huge leap with deep learning.
Right. The source is called deep learning, or DL, a more sophisticated subset. It uses these things called artificial neural networks, inspired by the brain.
Yeah, ANNs. They're structured in layers. That's where the deep part comes from. These layers allow the models to learn hierarchies of features, processing information at increasing levels of abstraction.
Okay, so it's like layers of understanding.
Kind of. This layered structure lets deep learning tackle incredibly complex tasks that were really hard before. Things like generating realistic images from scratch, understanding nuances in language, or even helping discover potential new drugs.
Wow, and this is where some really key figures come in, right? The sources mention the godfathers of AI.
That's right. Jan LeCun, Geoffrey Hinton, and Yoshua Bengio. Their work, especially in the 90s and early 2000s, was absolutely foundational. They figured out how to effectively train these deep, multi-layered neural networks.
That sounds crucial.
It was game-changing. Their research really unlocked the potential of deep learning, which is why they shared the Turing Award in 2018. That's like the Nobel Prize for Computer Science.
Yeah.
It recognized how fundamental their contributions were.
So their work really paved the way for the AI boom we're seeing now. And the sources also mention how these algorithms are actually trained. There are different methods.
Yep, three main approaches. First is supervised learning. Think of it like learning with a teacher or answer key. You feed the AI data that's already been labeled with the correct answers. So you show it pictures, and each one is labeled cat or dog. The AI makes a guess, you compare it to the label, and you adjust the AI so it gets better at guessing correctly.
Makes sense. Learning from labeled examples. What's unsupervised learning?
That's more like learning without a teacher. You give the AI a whole bunch of data, but without any labels. Its job is just to find patterns or structures hidden in the data itself.
So what would it do with the animal pictures?
It might start grouping images together based on shared features. Maybe it finds clusters of furry things with pointy ears or things with feathers and wings without ever being told those clusters are cats or birds. It discovers the inherent structure.
Interesting. Finding patterns on its own. And the third one?
Reinforcement learning. This is learning through trial and error, basically, like teaching a dog tricks with treats. The AI operates in some environment, takes actions, and gets feedback, either rewards for good actions or penalties for bad ones. It learns over time to choose actions that maximize its total reward. This is how they train AIs to play games, for instance, rewarding winning moves, penalizing losing ones.
Got it. Supervised, unsupervised, and reinforcement learning. So these sophisticated algorithms are the first pillar. The second is data. And the sources just keep emphasizing AI needs huge amounts of data.
Oh, absolutely critical. You can't overstate this, especially for ML and DL models. Their performance is massively dependent on the sheer volume and the quality of the data they're trained on. Generally, more data means better, more accurate models.
And the amount of data being created is, well, it's staggering. There's that statistic from 2013, 90% of the world's data then have been generated in just the last 2 years.
Wild, isn't it? And that pace is only accelerated. There was a projection mentioned from the European Parliament estimating we could hit 175 zettabytes of global data by 2025.
175 zettabytes. I can't even picture that.
It's almost impossible to grasp. For context, that's a 175-fold increase compared to 2010 in just 15 years.
How do the sources help visualize that?
Okay, think of a high-end laptop with a 1 terabyte drive. 175 zettabytes is the equivalent of 175 billion of those laptops.
Billion. Okay.
Or maybe this helps. It's roughly like generating 21 laptops worth of data every year for every single person on Earth.
21 laptops per person per year. Wow. Okay, that puts it in perspective. No wonder they had to invent new data units in 2022.
Exactly. The ronabyte and the quetabyte. First new prefixes in over 30 years. They expect we'll need them for the next couple of decades at least. That tells you something about the expected growth.
So where's all this data coming from? What's driving this explosion?
Several big things. First, just the sheer number of devices connected to the internet. Phones, computers, sensors, everything. We're talking nearly 30 billion devices in 2023. That's more than 3 times the global population. Each one is a potential data source.
More devices, more data points.
Yep. Second, social media. Just think about Facebook, Instagram, TikTok, YouTube. The amount of text, photos, videos uploaded every single second is astronomical.
Billions of messages, posts.
Right. WhatsApp was doing 100 billion messages a day back in 2020. TikTok and YouTube videos make up more than half of all internet traffic now. And all that social data. It's gold dust for AI trying to understand how humans talk, what we like, how we behave.
It's like a giant ongoing study of humanity.
In a way, yes. And third, they're all the new ways we're collecting and storing data. Sensors in smart cities monitoring traffic or energy, smart grids, connected transport systems, and the whole Internet of Things, IoT.
IoT, like smart fridges and thermostats.
Exactly. Everyday objects connected online. The sources say about half of those nearly 30 billion connected devices are IoT devices. Things like connected home appliances or connected cars sending back data, all contributing to the flood.
So everything's becoming the data source. And this massive volume enables specific AI tricks, right?
Definitely. All this data is what powers personalization. AI systems analyze your past clicks, your purchases, your viewing habits, your interactions, and compare them to millions of others to give you those tailored suggestions. E-commerce, social media feeds, streaming services, they all rely on it.
That's why the recommendations can feel so spot on, or sometimes a bit too spot on.
Yeah. And it's absolutely vital for natural language processing, NLP, especially for the big, large language models, the LLMs, behind things like ChatGPT. They learn grammar, context, meaning, style, all by processing truly vast amounts of text from books, articles, websites, social media. That's how they get so good at understanding and generating human-like language.
All this data needs a place to live, though. The sources mention things like data warehouses, data lakes.
Right. Data warehouses, data lakes, data lake houses. These are just different ways organizations structure and store their massive data sets, depending on whether the data is structured or unstructured and how they plan to use it. The key point is, these are the reservoirs where AI gets applied to find insights, automate things, analyze customer sentiment from social media, predict trends, optimize pricing, you name it.
Okay, so algorithms need data. And the third leg of the stool is compute, the processing power.
Yes, you need serious muscle to crunch through those huge data sets and run those complex algorithms, especially for training deep learning models. It takes a lot of computational power, and getting it done fast is crucial. The history here ties right back to the hardware.
Back to the 60s and Gordon Moore, Moore's law.
Exactly. Moore's observation about transistors doubling roughly every 2 years drove decades of progress in CPUs, the main processors in computers and phones. They got faster and cheaper, which was amazing. But for the kind of math AI needed, especially deep learning, something else was needed, something that could do lots of calculations at once.
Parallel processing. And that's where GPUs came in.
The graphics processing unit,
Yeah.
GPUs, popularized by companies like NVIDIA back in the 90s, initially for making video games and movie graphics look super realistic and run fast.
Right, for gaming.
Yeah. But the key was their design. Unlike CPUs, which are generally good at doing tasks one after another very quickly, GPUs were built to handle thousands of simpler calculations simultaneously, in parallel. Perfect for rendering pixels on a screen.
And it turned out that parallel processing was exactly what deep learning needed.
Bingo. The core math involves tons of matrix multiplications and other operations that can be done in parallel. GPUs were just vastly better suited for it than CPUs. It was almost a lucky accident for AI research.
So hardware design for, like, making dragons look cool in games accidentally became the engine for the AI revolution. That's pretty wild.
It really is. And the demand for these GPUs for AI has just exploded. It's a huge reason why NVIDIA became $1 trillion company in 2023. They were in the right place with the right tech.
And this reliance on specialized chips is now a big deal geopolitically, the sources say.
Oh, absolutely. Making these cutting-edge chips is incredibly complex and expensive, and the manufacturing capability is concentrated in just a few places, mainly Taiwan. So you've got the US, China, the EU, all seeing chip production as strategically vital. They're pouring billions into domestic chip initiatives like the Made in China 2025 plan, the EU CHIPS Act, the US Chip PS and Science Act. It's a major global competition.
A strategic race for the hardware that powers AI. And Google even designed its own AI chip.
They did. The Tensor Processing Unit, or TPU. They unveiled it back in 2016. TPUs are application-specific integrated circuits, or ASICs, specifically designed to accelerate machine learning workloads. They're particularly good at the matrix math that's central to neural networks, often even faster than GPUs for those specific tasks.
The sources had a good analogy for the difference in speed.
Yeah, the printing press one. If a CPU is like printing one letter at a time, a GPU is like printing a whole line at once.
And a TPU is like printing the whole page.
Exactly. That specialization gives them a huge speed advantage for training and running big AI models. They power a lot of Google's own services, like Translate or search features, and the latest versions can do hundreds of trillions of calculations every second.
400 trillion per second on one chip. But the real power for training the biggest models comes from linking thousands of these together.
That's right. For the really monster AI models, like the ones behind advanced chatbots or image generators, you need supercomputers. Yeah. That means connecting thousands, sometimes tens of thousands, of GPUs or TPUs together in massive clusters.
Like the one Microsoft built for ChatGPT.
Yep, that's a prime example mentioned. Built in 2020, used 10,000 GPUs, cost millions of dollars, and at the time, it was ranked among the top 5 most powerful supercomputers in the world, just to train one model.
10,000 GPUs. The scale and cost are just enormous.
They are. We're talking dedicated data centers, massive power consumption, huge cooling systems. It costs a fortune to build and run these things. And that does raise concerns about access, Can universities or smaller companies or governments in less wealthy countries afford this kind of compute? It risks widening the gap.
But the sources also say you don't necessarily need to own a supercomputer these days.
Right. That's where cloud computing comes in. The big cloud providers, Google Cloud, Microsoft Azure, Amazon Web Services, IBM Cloud, they've built this massive AI infrastructure, and they rent out access to it.
So you can essentially lease time on these supercomputers.
Exactly. You can access powerful AI models, huge amounts of processing power, memory, storage, networking, all on demand, paying for what you use. It definitely helps democratize access to high-end AI capabilities, making it feasible for many more organizations and researchers.
Okay, so wrapping up the building blocks. It's the clever algorithms, especially ML and DL, fueled by vast amounts of data, running on incredibly powerful compute hardware, GPUs, TPUs, supercomputers, often accessed via the cloud. That's the magic combo.
That synergy is absolutely fundamental. You need all three working together to get the kind of AI performance we're seeing today, And it's the rapid improvement in all three areas that's driving the current acceleration.
Right. Now that we have a better sense of the what and how, let's rewind and look at the when and who. The history. The sources paint a picture of a journey with ups and downs, right? Springs and winters.
Exactly, it wasn't a straight line. The history of AI is full of brilliant ideas, periods of intense optimism and funding the AI springs, followed by periods of disillusionment, budget cuts, and slower progress, the AI winters. It's been a cycle.
And the very idea of intelligent machines goes way back.
Oh yeah, centuries. The sources even point to Jonathan Swift's Gulliver's Travels back in 1726.
Really? How so?
He described this satirical device called the engine in the Academy of Legato. They had all these words on wooden blocks connected by wires, and by turning handles, he would rearrange them into fragmented sentences, supposedly generating new knowledge. It was satire, but it kind of anticipated algorithmic text generation in a weird way.
Huh. From satire to early actual machines, like that chess player.
Leonardo Torres y Quevedo's El Ajedrecista from 1914, an electromechanical automaton. It couldn't play a full game, but it could handle a simple king and rook versus king endgame. It moved the pieces itself and even had a light signal if the human made an illegal move. A very early example of automated decision-making.
Amazing for 1914. Then, closer to modern computing, the Atanasoff-Berry computer.
The EBC, yeah. Developed around 1939 at Iowa State. It wasn't programmable like later computers, but it was one of the very first electronic digital computing devices. It pioneered key ideas, using binary numbers, using electronic circuits for calculation, and separating the memory from the processing unit. Really important foundational concepts.
And then the idea of artificial neurons emerged.
In 1943, McCulloch and Pitts published a super influential paper. They proposed a simplified mathematical model of how biological neurons might work, creating the concept of an artificial neural network. It was theoretical, but it laid the groundwork for thinking about computation in a brain-inspired way, the whole connectionist approach.
So the theoretical seeds were being planted. Then came the 50s and 60s, what the sources call the birth of AI, the first AI spring. And Alan Turing looms large here.
Absolutely central. Alan Turing. His code-breaking work at Bletchley Park during World War II, building and using early computing machines like the Bonda to crack the German Enigma code, really put him at the forefront of thinking about machine capabilities. He's considered a founding father of both computer science and AI.
And his famous 1950 paper, Computing Machinery and Intelligence.
That's the one. He tackled the question, can machines think? Head on. And instead of getting bogged down in defining thinking, he proposed a practical test, the imitation game, now known as the Turing test.
The Turing test, explain that again simply.
Sure. Imagine a human judge having two text-based conversations, one with another human, one with a machine. If the judge can't reliably tell which is which, then, Turing argued, the machine could be said to be thinking or exhibiting intelligent behavior.
So it's about convincingly imitating human conversation.
Exactly. It set a benchmark, a target for the field. Now, the sources are quick to point out, no machine has definitively passed a rigorous Turing test yet, although modern chatbots are getting scarily good.
Right.
And there are criticisms too, right? Like Lady Lovelace's objection from the 19th century that machines can only do what we program them to do. They can't originate anything new, though modern ML kind of challenges that now. And philosophers debate whether imitating intelligence is the same as having it.
Still, it was a hugely influential idea even early attempts were telling.
Yeah, the transcripts from the Loebner Prize contests, which were based on the Turing test, show that even in the mid-2000s, the winning chatbots were still pretty easy to spot as machines. They lacked real understanding and common sense.
But the test definitely focused minds. And just a few years after Turing's paper, the field got its name.
That's right. At the Dartmouth Summer Research Project on Artificial Intelligence in 1956, an 8-week workshop funded by the Rockefeller Foundation. John McCarthy actually coined the term artificial intelligence to the proposal.
And key people were there.
Oh yeah, the pioneers. Marvin Minsky, McCarthy himself, Nathaniel Rochester, who designed IBM's first commercial scientific computer, Claude Shannon, the founder of information theory, a real who's who.
And their goal was ambitious.
Totally. They wanted to bring together researchers from different areas, logic, cybernetics, information theory, to kickstart a new field dedicated to making machines simulate human intelligence. Learning, language, problem solving, the works. And this era was full of optimism.
The sources mentioned bold predictions.
Yeah, it really did. Fueled by the Dartmouth spirit and some early successes, people were predicting fully intelligent machines within a generation. And we did see some intriguing early programs.
Like Eliza, the therapist chatbot.
Yeah, Joseph Weissenbaum's ELIZA from 1966. It famously simulated a Rogerian psychotherapist. It worked using clever pattern matching and keyword spotting to turn the user's statements back as questions. It didn't understand anything, but it could seem remarkably conversational. Some people apparently got quite attached to it.
Wow. And SHRDLU, that sounds like a mouthful.
SHRDLU, developed between 68 and 70 by Terry Winograd. It was a landmark program that operated in a simulated blocks world on a computer screen. You could type commands in natural English like pick up the red block or put the blue pyramid on the green cube, and it would understand, execute the actions in the simulation, and answer questions about its world. Very impressive for the time.
So early glimmers of language understanding and interaction. But the reality didn't quite match those bold predictions.
Exactly. These programs worked only in extremely limited toy worlds. Scaling them up to handle the complexity and ambiguity of the real world proved incredibly difficult. The hype outran the progress.
Which led to the first AI win.
Precisely. By the mid-1970s, funding agencies started getting skeptical. Progress seemed slow. Practical applications were scarce. Key critical reports, like the ALPAC report in the U.S. looking at machine translation, and particularly the Lighthill report in the UK in 1973, basically concluded that AI hadn't delivered on its promises and wasn't likely to soon. Funding dried up, research slowed down. First, AI winter.
Expectations crashed. But the work didn't completely stop, did it? The focus just shifted.
Right. The pendulum swung towards a different approach in the 70s and 80s. Symbolic AI and what became known as expert systems.
Expert systems, what was the idea there?
Instead of trying to create general intelligence from scratch, the idea was to capture the knowledge and reasoning processes of human experts in specific narrow domains, like a doctor diagnosing diseases or a geologist identifying mineral deposits.
So encode human expertise into rules.
Exactly. You'd build a knowledge base containing facts and rules, like if symptom X and symptom Y, then likely condition Z, and an inference engine that could use those rules to answer questions or solve problems within the domain.
And did they work?
They had some notable successes. Dendril, developed in the 60s, could infer the structure of chemical compounds. XCON helped configure complex computer systems for DEC in the 80s, saving them millions. NYCIN could diagnose bacterial infections. There was Prolog, a logic programming language that became popular for this kind of work.
So practical applications in specific areas, but they had limits too.
Big time. The knowledge acquisition bottleneck was a huge problem. Getting all that expert knowledge out of human heads and into computer code was incredibly difficult, slow, and expensive. These systems were also very brittle. They worked okay within their narrow domain, but failed completely if they encountered something slightly outside it. They lacked common sense, couldn't handle uncertainty well, and verifying they were correct was hard. Plus, legal worries. What if an expert system gave bad medical advice?
Right, lots of challenges. But there was still international interest, like Japan's big project.
Yeah, the fifth generation computer systems project, launched by Japan in 1982. It was a massive 10-year effort, aiming to build computers based on logical reasoning, capable of natural language understanding and running expert systems. It caused quite a stir globally.
Spurred competition.
Definitely. The U.S. government, through DARPA, responded with its own strategic computing initiative, pouring more money into AI research, particularly into areas like machine vision and parallel computing. But even with this push,
Another winter was coming.
yeah, seems to be the pattern. Researchers like Roger Schank and Marvin Minsky themselves warned in 1984 that expectations were again getting overblown, particularly around expert systems. And sure enough, by 1987, the expert system market had collapsed, funding dwindled again, and the second AI winter set in.
History repeating itself. But again, important work was still happening underneath, right? Things that would matter later.
Absolutely. Crucial foundational work continued. The connectionist approach neural networks started making a comeback. John Hopfield introduced Hopfield nets in '82, which had interesting memory properties. And crucially, the backpropagation algorithm, which allowed for training deeper networks, became widely understood and applied around 1985 thanks to work by Rumelhart, Hinton, and Williams. That was massive for reviving neural nets.
Backpropagation. That sounds important.
Hugely. It solved a key problem in training multi-layer networks. And there were other milestones, too. The Stanford cart, a robot, managed to autonomously navigate across a cluttered room way back in 1979.
Wow, early self-driving tech.
Kind of. And Judea Pearl's work on Bayesian networks in 1988 was fundamental for dealing with probability and uncertainty in AI, earning him a Turing Award later. There was Rollo Carpenter's chatbot Jabberwocky in '88, designed to learn through conversation. And significantly, IBM shifted its approach to machine translation in '88, moving away from hand-coded rules towards statistical methods trained on large bilingual data sets, like Canadian parliamentary records. That really pointed towards the future of data-driven AI.
So even during the winter, key pieces were falling into place. But the public probably didn't notice much until some big flashy milestones hit the headlines again.
Exactly. That takes us into the late '90s and the 2000s. The first really big one the sources highlight is IBM's Deep Blue.
Beating Garry Kasparov at chess in 1997, I remember that. It felt huge.
It was a landmark moment. Deep Blue was essentially a massively powerful, specialized expert system for chess. It used brute force computation, evaluating 200 million positions per second, combined with stored chess knowledge to look incredibly deep into the game. It proved a machine could beat the human world champion in a game requiring deep strategy. Still, it was very specific to chess.
And then IBM topped that with Watson on Jeopardy.
In 2011, yeah. Watson winning Jeopardy was different. It wasn't just calculation. It required understanding natural language, the often tricky, pun-filled Jeopardy clues, searching a vast database of knowledge. It was trained on encyclopedias, dictionaries, news articles, etc., evaluating evidence and buzzing in with the right question. It showcased major advances in NLP and information retrieval.
So Deep Blue was calculation, Watson was understanding language and knowledge. Both were impressive, but still kind of specialized supercomputers, not everyday AI.
Precisely. They showed what was becoming possible at the high end, but the technology wasn't in people's pockets yet. That started to change soon after.
Which brings us to the current era. Starting maybe in the 90s, but really taking off in the 2010s, the return of machine learning, the rise of deep learning, powered by all that data and compute we talked about. The sources call it the AI fall, like a harvest.
Yeah, the harvest of the fruits of all that earlier work, especially on neural networks and statistical methods. This is the era where it all came together.
Yeah.
Early signs were things like Jan LeCun's work using convolutional neural networks, CNNs, to read handwritten zip codes back in 1989.
CNNs, heard that term.
They became huge for image recognition. And then Geoffrey Hinton's work around 2006 on better ways to train deep networks really kicked off the modern deep learning era.
And they needed data. Lots of it.
Enter ImageNet. Started in 2007 by Fei Lai and her team. It was a massive project to create a huge database of images, all meticulously labeled by humans. It became the standard benchmark dataset for training and testing computer vision models. Having that data was absolutely critical for deep learning success in vision.
So better algorithms met big data, and then the hardware caught up.
Exactly. That crucial discovery around 2009 showing that GPUs were way, way faster than CPUs for the math involved in deep learning. That was the accelerator. Suddenly, researchers could train much bigger, deeper models on much more data, much faster. That unlocked the breakthroughs of the 2010s.
And we started seeing AI conquer games even harder than chess.
Oh yeah. DeepMind's AlphaGo beating Lee Sedol, the world Go champion, in 2016. That was a shocker for many. Go has far more possible positions than chess. It relies more on intuition. People thought AI mastering Go was decades away. AlphaGo used deep learning and reinforcement learning in novel ways.
And AlphaGo didn't stop there.
Nope. It evolved into AlphaZero in 2017. AlphaZero learned Go, chess, and shogi, Japanese chess, entirely from scratch, just by playing millions of games against itself. No human data needed. Within hours or days, it reached superhuman levels, discovering strategies humans hadn't. Then AlphaStar tackled the incredibly complex real-time strategy video game StarCraft 2 in 2019, reaching Grandmaster level and beating pros.
It wasn't just about games, though. These showed fundamental advances in learning complex strategies. And AI started appearing in consumer tech.
Right. Apple launching Siri on the iPhone in 2011 was a big step. It put a conversational AI, using natural language processing and machine learning, into millions of hands. It made AI feel interactive and accessible.
And then came the really big architectural shifts that led to today's generative AI boom.
Two huge ones mentioned. First, the transformer architecture. Introduced in a landmark 2017 paper titled, brilliantly, Attention is All You Need.
Attention is all you need. Love that title.
Right. This new architecture, based on a mechanism called self-attention, proved incredibly powerful for handling sequential data, especially text. It's the foundation for almost all the large language models like GPT that are amazing us today. That paper is seen as a major turning point for generative AI.
So transformers were key for language. What was the other one?
Generative Adversarial Networks, or GANs. Developed by Ian Goodfellow and others around 2014, GANs involve two neural networks, a generator that creates fake data, and a discriminator that tries to tell the fake data from real data. They compete against each other, and in the process, the generator gets incredibly good at producing realistic-looking synthetic data images, music, whatever it's trained on.
So transformers for understanding and generating sequences like text, GANs for generating realistic outputs like images, these enabled AI to create stuff.
Exactly. Create new content, not just analyze existing data. And we saw AI hitting other benchmarks too, like Alibaba's AI beating humans on a reading comprehension test in 2018.
Which brings us right up to the explosion we're seeing now. Generative AI taking center stage from around 2022 onwards.
This is the current wave. Generative AI, based on these massive foundation models trained on internet-scale data, capable of producing text, images, code, audio, video from simple text prompts.
And the moment it really hit the mainstream, the sources agree, was ChatGPT.
OpenAI releasing ChatGPT to the public in November 2022. That was the catalyst. Suddenly, anyone could interact with a powerful, versatile AI chatbot through a simple web interface. Its abilities to write code, explain, converse, it just blew people away.
And it spread like wildfire.
Unbelievably fast. 100 million users in just 2 months. At the time, the fastest growing consumer app ever. Unlike Deep Blue or Watson, this wasn't some remote supercomputer. It was right there on your screen. It made the power of modern AI tangible for hundreds of millions.
And then came the others, Google Bard, now Gemini, Microsoft Copilot.
Exactly. The AI chatbot race was on. Google, Microsoft, Baidu, and China with Ernie. Everyone released their own versions. This direct access really fueled the current global fascination.
And the creative results are just getting better and better.
Astonishingly so. The sources contrast the kind of distorted AI portraits from just 2018 with the photorealistic images or sophisticated paintings AI can generate now. Think of those viral images of the Pope in the puffer jacket, the fake Trump arrest photos. Convincing, generated quickly, widely shared. And the software to do this is now easily available.
It's disrupting creative fields too.
For sure. The Grammys now allowing AI-assisted music. Paul McCartney using AI to clean up and isolate John Lennon's vocals for that final Beatles track now and then. Artists like Grimes letting people use AI versions of her voice and offering to split royalties. It's becoming a tool, a collaborator, a disruptor.
And the investment followed the hype.
Massively.
Yeah.
Scientific papers on generative AI skyrocketed. Venture capital poured in $12 billion just in the first half of 2023 for generative AI startups.
The momentum is huge.
And the progress hasn't stopped. Models keep getting better, constantly. Google's MUM model, improving search across languages using text and images. Tesla pushing its full self-driving beta using deep learning. Then you have Google's Gemini 1.5 model in 2024 with a massive context window. It can process and understand incredibly long texts or even videos.
And OpenAI's Sora for video generation.
Yeah, Sora generating surprisingly coherent and detailed minute-long videos just from text prompts. That was another wow moment in early 2024.
And now it's being baked right into our core devices, like Apple putting AI features and ChatGPT into iPhones with Apple Intelligence.
Announced June 2024, yeah. Making Siri smarter, helping with writing, summarizing, bringing advanced AI directly into the operating system. It shows how deeply integrated this is becoming.
And even this very deep dive, the sources mentioned tech like NotebookLM deep dive, using multimodal AI to turn source material into audio presentations. It's all happening fast.
It's a perfect meta example, isn't it? AI helping us understand AI. So yeah, the history shows this long journey, deep roots, cycles of hope and disappointment. But persistent research, especially on neural nets, finally unleashed by that perfect storm of data and compute, leading to this accessible, powerful, generative AI moment we're in right now.
It really is a story of cumulative progress, different ideas, different technologies converging and accelerating. From abstract ideas to machines that can write poetry, it's quite a leap.
An incredible leap.
But, and this is a big but, this power and speed come with real challenges, real risks. The sources spend a lot of time on the downsides and the need for caution.
They absolutely do. It's not all sunshine and roses. The potential is huge, but the sources are very clear. There are significant concerns, and we urgently need guardrails, as they put it.
And one of the most immediate dangers seems to be disinformation.
Yeah, that's a major worry, especially around elections and public discourse. AI makes generating convincing fake news, fake images, fake videos incredibly easy and cheap. We saw those examples, the AI image of the Pope in the puffer jacket, the fake Trump arrest pictures.
So real and spread so fast.
Exactly. Created on home computers, basically, with readily available tools. It showed how easily AI can be used to mislead people, erode trust, and manipulate opinion. A serious threat.
And related to that are deepfakes, right?
Very closely related. Deepfakes are those AI-generated videos or audio clips that make it look like someone said or did something they never did. The sources mention they can be used harmlessly, like that Lionel Messi deepfake used in Pepsi ads with his permission.
So sometimes it's authorized for entertainment or ads.
Yes, but the real concern is the malicious use. Creating fake news reports, impersonating people for fraud. Imagine a fake audio call from your boss asking for a money transfer. Generating spam, phishing attacks, or even creating non-consensual explicit content. The ability to convincingly fake someone's voice or image is deeply problematic.
Definitely. Another big issue flagged is bias in AI systems.
This is fundamental. AI learns from data. If that data reflects existing biases in society, racial, gender, whatever that AI, will learn those biases. And often, it can even amplify them.
So the AI isn't biased itself, but it learns our biases.
Precisely. The sources give examples like facial recognition systems being less accurate for people with darker skin tones, likely because they were trained on data sets skewed towards lighter skin, or AI tools used in hiring or loan applications showing bias against certain groups because they learned from biased historical data, or even judicial systems using AI tools trained on past rulings that reflect systemic biases.
That's deeply concerning. It means AI could actually perpetuate or worsen inequality if we're not careful.
It absolutely could. Dealing with data bias, ensuring fairness in algorithms, making systems transparent, it's a huge area of research and ethical concern.
And then there's this weird thing the sources call AI hallucinations. What's that about?
Yeah, it sounds strange, doesn't it? It basically means when an AI, particularly a generative one like a chatbot, produces information that sounds plausible, even confident, but is actually completely wrong or made up.
It just invents things.
Essentially, yes. It might happen if the AI doesn't really know the answer, but tries to construct one based on patterns it learned, or if its training data was incomplete or contradictory. The sources gave that example where an AI chatbot summarizing reports got the summaries right, but just hallucinated incorrect publication dates.
Wow. So you really can't trust everything it says.
Definitely not blindly. It underscores the need for human oversight and verification, especially for important information. You need to treat AI outputs critically.
Good advice. Don't just copy-paste.
Please don't. And then there are adversarial attacks.
That sounds sinister, like deliberately messing with the AI.
That's exactly what it is. Crafting specific inputs designed to fool an AI system. The classic example is taking an image, say, of a panda and making tiny changes invisible to the human eye that cause the AI to confidently misclassify it as something totally different, like an ostrich.
Just tiny changes can throw it off completely.
Sometimes, yes. And think about the implications for safety. If attackers could put special stickers on stop signs that trick self-driving cars into seeing them as speed limit signs, that's incredibly dangerous. Securing AI systems against these kinds of attacks is another major challenge.
Okay, so we've got disinformation, deepfakes, bias, hallucinations, adversarial attacks. Quite a list of risks, which leads directly to the need for rules, for guardrails, for regulation, right?
Absolutely. The sources are unanimous on this. We need ways to manage these risks as AI becomes more integrated into society. And this can involve everything from formal laws passed by governments to industry codes of conduct and technical best practices.
And the sources look at regulation from different angles, like micro, meso, macro.
Yeah, starting at the micro level, regulating the algorithms and the companies making them. Maybe not trying to regulate AI as a concept, but setting standards for how algorithms are trained, tested, and audited for safety and fairness, similar to how we regulate physical products. Maybe even things like warranties for AI performance.
And figuring out who's responsible when things go wrong.
That's a huge piece, accountability. If an autonomous system causes harm, who pays? The developer, the owner,
Yeah.
the user. It's complex. But the sources also caution that regulating algorithms might not stop bad actors deliberately misusing the tech for things like fake news or hacking.
Okay, then the meso perspective. That's about jobs.
Yes, the impact on employment. This is a recurring theme. Automation already hit manufacturing jobs hard. Now, AI looks poised to automate tasks in many white-collar and professional fields. Think about AI analyzing medical images better than radiologists, or AI doing legal document review faster than paralegals.
So jobs requiring cognitive skills are potentially threatened.
That's the concern. Will AI displace more jobs than it creates? And will people have the skills needed for the new jobs that do emerge? The sources even mention that sci-fi novel Snow Crash as a kind of cautionary glimpse of a future with mass unemployment.
What kind of regulatory responses are discussed for that?
Things like requiring companies to reinvest some automation savings into worker retraining, or governments maybe limiting the pace or scope of automation in certain sectors, or even exploring ideas like reduced working hours to share the available work, though that's complicated. Universal basic income is also mentioned as a potential safety net, but it faces huge hurdles.
Complex societal shifts. And the macro perspective, that sounds even bigger. Democracy, peace.
Right. This goes to the core of state power and control. The sources ask, who guards the guards? How do governments use AI? The example given is China's social credit system, which uses mass surveillance, big data, and AI to monitor and score citizens' behavior, influencing their access to services and opportunities.
Using AI for social engineering on a massive scale.
That's one interpretation. But there's pushback too. The sources mention things like San Francisco banning government use of facial recognition, or researchers working on ways to digitally hide from surveillance. It's an ongoing technological and societal struggle.
And different countries are taking different paths on regulation overall.
Definitely. You see a contrast between, say, the US and China, which have generally favored lighter regulation to spur innovation, and the EU, which has taken a more cautious, rights-focused approach with things like GDPR data privacy rules, and now the Comprehensive AI Act. It's a balancing act between fostering economic growth and protecting citizens' rights and privacy.
And because AI is global, does local regulation even work?
That's a key point the sources make. For AI to be regulated effectively, especially concerning risks like autonomous weapons or global disinformation, you probably need international cooperation and coordination. Just like with arms control or financial crime, national rules alone might not be enough.
Beyond formal laws, there's also a big push for AI ethics, trustworthiness.
Huge focus on this globally. Events like the first AI Safety Summit in the UK in late 2023 show governments trying to get ahead of the risks. International bodies like the UN and G7, individual countries, and tech companies themselves are all developing ethical guidelines and principles for responsible AI development and deployment.
The sources mention fate, fairness, accountability.
Transparency and explainability. Fate. These are core concepts. Can we ensure AI systems are fair and don't discriminate? Can we hold someone accountable when they go wrong? Can we understand how they make decisions? Transparency. And can they explain their reasoning? Explainability. These ideas are central to frameworks like the EU's guidelines for trustworthy AI.
And those EU guidelines include other principles too.
Yes, things like human agency and oversight, keeping humans in the loop, technical robustness and safety, privacy, diversity, societal well-being, and accountability. Many organizations have their own list too, the Beijing AI principles, OECD principles, Google's AI principles, which explicitly commit not to develop AI for weapons or harmful surveillance. It's an active, evolving field of discussion.
So, building ethical, trustworthy AI is a massive ongoing effort.
Absolutely critical for public acceptance and ensuring AI benefits society. But going back to the building blocks, data and compute their importance also highlights another major challenge: inequality.
The digital divide. We touched on this.
Right. AI thrives on data and processing power. If you don't have good internet access, affordable devices, or the skills to use them, you're left behind. The sources quote ITU data. In 2022, over a third of the world's population, 2.6 billion people, had never used the internet.
A third of the planet is essentially excluded from the digital world, and therefore from much of the AI revolution.
It's a stark reality. The goal of universal and meaningful digital connectivity, making sure everyone has safe, affordable, productive online access, is crucial. Otherwise, AI could just make existing inequalities worse. And the cost barrier is real in the poorest countries. Mobile broadband can eat up a huge chunk of average income.
Are there efforts to bridge this gap specifically for AI?
Yes, initiatives are starting. The sources mention the UK and Canada promoting an AI for development vision, aiming to boost AI skills, infrastructure, and innovation in lower-income countries, starting with Africa. The idea is to make sure the opportunities of AI are shared globally.
That quote comes to mind again. The future is already here, it's just not evenly distributed yet. Seems to fit perfectly.
William Gibson. It really does capture the situation with AI and the digital divide. And it's not just about access to tech, it's also about skills. There's a huge digital skills gap.
Even in developed nations.
Yes, everywhere. A 2023 survey mentioned found only 13% of workers across many countries got any AI training last year, even though job postings needing AI skills surged. People want the training, but it's often not available.
So companies need AI skills, workers want AI training, but the training isn't happening enough.
Seems to be a disconnect. And another survey suggested training often isn't reaching the frontline workers who might feel most threatened by automation. Experts are saying companies must invest massively in reskilling and upskilling their workforce. IBM estimated something like 40% of workers might need retraining in the next few years because of AI and automation.
40%. That's enormous. It really highlights that the human element, education, training, adaptation, is just as critical as the technology itself.
Couldn't agree more. You can't have a successful AI future without preparing the people.
Finally, the sources touch on some really deep, almost philosophical questions that AI raises, back to the nature of intelligence consciousness.
Yeah, it forces us to confront big ideas. Will AI ultimately enhance human capabilities, leading to a kind of symbiosis, as some like Raymond Kurzweil predict? Or does it pose existential threats, as figures like Elon Musk have warned?
Two very different futures there.
And it makes old philosophical thought experiments suddenly very real, like the trolley problem. The runaway trolley. Do you switch tracks to save 5 people but kill one? Self-driving cars might face mathematically similar dilemmas in unavoidable accidents. How do programmers code ethics into a machine?
The programmer becomes the ethicist.
In a way, yes. And then there's John Searle's Chinese room argument. Imagine someone locked in a room who doesn't know Chinese but has a giant rule book telling them which Chinese symbols to output in response to symbols slipped onto the door. They could perfectly simulate understanding Chinese conversation, but do they really understand? Searle argued, computers manipulating symbols based on rules don't truly understand either.
Does syntax equal semantics? Does processing mean understanding? Deep stuff.
It is, and the sources even glance at really out there ideas, like Kurzweil's speculations about nanobots mapping our brains so we can upload our minds to computers and achieve a kind of digital immortality.
Okay, that's definitely pushing the boundaries. But it does raise more immediate legal and ethical questions too, right? Like accountability again. If an AI diagnostic tool misses cancer or an AI air traffic system causes a crash, who's liable? Especially if the AI is complex and autonomous. Could a mistake even be intentional if AIs develop agency? Do we need laws for robots, like Asimov imagined?
These are the thorny questions legislators and ethicists are grappling with, alongside related issues like data sovereignty, who owns and controls the data that fuels AI, especially when it crosses borders.
It sounds like predicting exactly where this all leads is, well, pretty much impossible.
Extremely difficult. The sources bring up Amara's law. We tend to overestimate the effect of a technology in the short run and underestimate the effect in the long run.
So we get caught up in the immediate hype or fear, but the real deep changes might be slower and more profound than we expect.
That pattern certainly fits AI's history. Lots of hype cycles, but the underlying capabilities have steadily grown, and the long-term impact is likely to be immense, perhaps in ways we can't fully foresee yet.
Well, this has definitely been a deep dive. We've covered so much defining AI, breaking down the algorithms, data, and compute, tracing that whole roller coaster history of springs and winters, key people, key moments, right up to this generative AI explosion, and then digging into all the challenges, the risks, the ethical questions.
It really shows how decades of groundwork, plus those key technology accelerators, brought us here, to this point where AI is built on that powerful triad: smarter algorithms, massive data, and incredible compute power.
And remembering the people involved, from Turing and the Dartmouth pioneers to the godfathers like Hinton, LeCun, Bengio, and the teams behind Deep Blue, Watson, AlphaGo, ChatGPT, it's been a massive collective effort over time.
It really has. And things are moving incredibly fast right now. It feels like a truly pivotal moment.
So, maybe we can leave you, the listener, with this final thought pulling together everything we've discussed. We know the potential of AI is immense, but we also know the risks are real bias, hallucinations, disinformation, job disruption, the digital divide, all those ethical knots. So the big question is, how do we collectively steer this incredibly powerful technology? How do we make sure its benefits are shared widely, fairly, globally, and its harms are minimized? What's our role, your role, in understanding this, engaging with it, and shaping that future responsibly?
That's the challenge ahead of us all, isn't it?
Yeah.
A defining one for the coming years.